Welcome back. Till now, we have seen how to go about building the model. We have built a multiple linear regression model. The variables that we used is household income, number of family members, EMI or rent, and the flag variable that we have created. We have not considered the education qualification variable and number of earning members. That I am leaving it as a home exercise for you. Let me just execute this code once again. Okay, I've got the model. Having got the model, what is the next step? I wish to use this model to predict for new records. Before I get into the prediction, let me tell you, whenever you build a model, you will be given a data set. The way we build it is we split the data into two components. One is called a training set, other is called a testing set. You build the model on the training set, you learn from that data, that's why it is called training. You see the model performance on the training set, then you use the model, predict it on the testing set. You see the performance of the model on the testing set. You compare the two. If the testing model outcome is very close to what you got in the training, then you can say you have got a decently good model which is not overfitting. However, for now, I'm not going to get into these complexities of training and testing. We'll continue to use the same training set. On the same training set, we are going to see, we'll do the prediction and we'll see model performance measure. R square is already we have seen. We'll now come to root mean squared error, and then there are certain assumptions of heteroscedasticity. Error should be normally distributed, all of those things. Okay, so we have got this model. The model is stored in M linear mod. That's the name that we have been assigning it so far. Coming to prediction, I will have to call the predict function. The model object is M linear mod. That object has got a predict function. The data set for which you wish to do the prediction is the income expense, the data on which we have trained it. You have to pass the parameters which has been used to build the model, and the parameters should be in the same sequence in which you call the model function. Okay, so in the same sequence I have given the model parameters, I call the predict. Once I run this, the predicted estimate of the expense will all get stored here in the predict object. So here I'm now creating a empty data frame. In this empty data frame, I am storing what is the actual expense of the household and the expected, which is the predicted expense of the household, and then displaying that. So let me just quickly execute it. Having executed it, I can see that the actual expense of a household is 8,000, but the model has predicted is 9,365. Actual is 7,000, model has predicted 8,453. 4,500, here it is come as 1,744, and here you get a negative term also. Why has this negative term come into play? The reason why a negative term has come into play, because we had a variable which has got a negative beta. Our intercept is also starting with negative. Okay, so in that case we are getting a negative term. The corresponding income of that family probably might be very negligible. That's why we have come up with this negative term. In such cases, what you may say, if the negative term is coming up, you may put a certain value and say, okay, that is the expected expense, or make it 0. Some rounding off you can do. However, we are not going to get into all of those at this point of time. How good is the model? Let me see. Here, to see the model performance, what I'm going to do is on one axis, I'm going to plot the observed, which is the actual expense. On other axis, I'll plot the predicted. If both of them are very close to each other, you should get a line at a 45 degree. You should get a straight line. So here, when I make a plot, I can see that I'm getting a straight line. However, all of these dots, that is the error component. The dots which are away from the line is basically either over predicted or under predicted. Ideally, the error should be uniformly distributed. That is, error at any given cross section. What I mean by cross section is, if I take a cross section here and I take a cross section here, I take a cross section here, or I take a cross section here, all the dots should actually have been in a same range. That is, error should have been uniform distributed. However, this error is not uniformly distributed. This assumption is violated. Why it is violated? I'm very clear. The reason why it is violated is because of the EMI variable. Because EMI variable upfront we saw is not normally distributed. Violation of that assumption of linear regression started from there. Okay. Let's move forward. Here the objective is not that we are going to make a perfectly good model. To make a perfectly good model, I could have designed my data which is perfectly good, right? But the objective is to see what are the complexities that we face when building such a model. Model is often measured, the performance of the model is often measured by another model performance measure called root mean squared error. Root mean squared error is nothing but y minus y hat the whole square divided by n square root of that. Absolute value of root mean squared error does not have any meaning. Again, where it is useful, if you have got two models built on the same data set, if you have to say which is better, in that case the model with a lower root mean squared error is better compared to the model having higher root mean squared error. So the syntax to get root mean squared error of our model is this, where we are calling the metric, using the metric library, we are calling the mean squared error function. To mean squared error function, we are passing the actual observed value and the expected, which is the predicted value of the model, and it will give you the root mean squared error. The root mean squared error is coming as 5643. These dots which are away from the line are basically the residuals. The difference of this value from the line is actually the residual, that is observed minus expected value. Observed, which is the actual value, minus the predicted value, that difference is called residual error. So I'm computing the residual error. The assumption of a linear regression is residual should be normally distributed. So let's plot that. I'm making a histogram, and when I see the histogram, again it is very clear that it's not normal distribution. If it would be a normal distribution, these bars, these histograms should fall. Basically, I should get a pattern which is something like this. These histograms should have been reducing in the size as I go away, smaller and smaller. In that case, it would be a perfectly normal distributed. Again, I know the culprit variable is my EMI. You can try building the model without using EMI variable. Our two variables, which are monthly income and number of family members, both were normally distributed. From the graph we saw pair plots. you drop the EMI variable and then run the entire regression and see all of those things, you will see these may come more normal. Now the question as an analyst would be, should I be going with a model where all of the assumptions are perfectly matching, or should I be taking a model which is giving me relatively better R squared? These kind of questions we will keep facing as we build our models. At that point, you have to take a judgmental call. One of the judgmental call was very clear to me. I should have built two separate models. I should not be going with one single model because I know my EMI variable is not normally distributed. The segment of data where they are paying EMI, by doing a logarithmic transformation, I made that normal distributed. So in that case, I would build a separate model. All variables would have been normally distributed. The other segment where they were not paying EMI, that variable anyways I will not consider because all of them are at 0, which means I'll build a model ignoring the EMI variable. Probably I would have got a better outcome using two different models. These are the technical calls, decisions that we have to make. But for now, it is not normally distributed. One more thing that is important as we build the model is error term should not have any pattern. Error term should be randomly distributed. So what I'm doing is I'm making a plot of the residual component versus one of the independent variables. Ideally, you have to make this not with only one of the independent. You have to try this with all the independent variables, which means you have to make this scatter plot with independent variable. First independent variable I have taken is monthly household income. Then you have to run this with EMI. Then you have to run it with number of family members. If you have any other independent variables in the model, you have to run it with all of them and see that the error terms, the residuals, are randomly distributed. If there is a pattern, something like this, say, or if there is a pattern where the error terms are small in the initial, and then as the value of that term is, the independent variable is increasing, the error term is also increasing, which means that there is some explanatory element which is left in the error. The error which is left, residual, is not noise. It has got some explanatory power which I have not yet accounted in my model. In that case, we have to figure it out and solve that. For now, I can see my error does not have any pattern. Only thing is, this error is not having pattern. However, I can see the error has got low variance. The error has got low variance in the low income segment, whereas error has got high variance in the high income segment, which is very logical. People who are in the high income segment, they will have different way of spending. Some will be very lavish in spending behavior. Some would be very conservative in their spending behavior. But people who are in the low income, definitely they will have day-to-day livelihood expenses which cannot vary. So in that case, the variation in the low income is going to be less, which is also evident from the residual, and the variation in the high income is more wider. And this is where the concept of homoscedasticity and heteroscedasticity comes up. Let us just quickly understand the concept of homoscedasticity and heteroscedasticity. Homoscedasticity simply states that variance of the error term across observation is same, which means if I take a cross section of data where I have taken a cross section here, the error is equal. If I take a cross section here, error is equal. The variance of the error, that is this plot, normal distributed, the variance of the error at any point, if I take a cross section, the variance should be equal. However, this graph which is on the adjacent side, you can clearly see the variance of the error. If I take different cross section, here the variance at this point is less, here the variance is more wider, more spread out, and here the variance is further increasing. So there is a heteroscedasticity in the second graph. Again, the assumption of linear regression is error term should be homoscedastic, which means at any point you take a cross section, the variance should be same. From our graph, in the output, if I see, if I would have take a cross section here, my error variance would be slightly lower, and I take a cross section here, my variance is more, and if I take a cross section here, error variance is much more larger. All assumptions of a linear regression in practical scenario will never be met 100%. All assumptions of a linear regression in a practical scenario will not be met 100%. Now, if it is not going to be met 100%, what is the solution? The solution of this, I'll go back directly to my first graph here. It was very evident from this graph itself. When I created expense versus income, there is a less variance in the initial part of the data and more variance in the later part of the data. Once again, what it means is you create two different models. Now, either you create two different models, or once again, what you may have to do, create a flag variable, something to balance out, because there are two segments. There are two segments, high income segment, low income segment. So what I can do at this point, I can take a line here. I see that the variance in this range is less and the variance in this range is wider. I create a flag variable. Instead of creating two separate models, the flag variable 10 variable will account for that. Will it introduce multicollinearity? Yes, because the flag variable is created from an existing variable. It will introduce multicollinearity. Again, a judgmental call. Whether you want to have multicollinear variables, probably if it improves the overall model, I would go ahead and keep it. But all of these things require visual inspection of the data. So building a model is not simply executing the code. Building a model requires lots of in-depth observations of the patterns from data. From that patterns, thinking of what derived variables I can create by which the model can be further improvised. Finally, let me conclude the linear regression with a summary of the assumptions in a linear regression. The assumptions in a linear regression are there should be linearity between the dependent variable and the independent variable. To test for linearity, that's the reason why we created scatter plots. There should be homoscedasticity, that is constant error variance. So we have to create the residual plots. Normal error, the residual error, if I make a plot, it should be a normally distributed. we saw our histogram was not normally distributed. But to the extent possible, if we can bring it to normal, our model will be better. Independent error term should not have, sorry, error term should be independent. Independent error terms, I just explained independent error terms, which means there should be no pattern in the error. If there is a pattern in the error, which I showed by such a graph, what it means is, if I know this error, I can then predict the next error for the next record. If I know this two preceding errors, I can then predict the next error, which means the error terms are not independent. Typically, it comes in case when you have a time series data. If you have a time series data, the next month prediction is definitely a function of the previous month time period data. This is a concept of autocorrelation. If there is a relation between the next record and the previous record, there is an autocorrelation. So we should not have any autocorrelation. How do I know that there is no autocorrelation in my data? There is something called Dublin-Watson statistic that we have. So if I see that, let me just quickly observe. So if the Durbin-Watson statistics is around 2, you can be confident that there is no autocorrelation in your data. If it is 4, it means there is a positive autocorrelation. If it is towards 0, it is negative autocorrelation. We are at around 2, so we know our model does not have any autocorrelation. No multicollinearity. We have ensured there is no multicollinearity in our model by using the variance inflation factor. Exogeneity. No omitted variable bias. What it means is, let me first read the definition and then try to help explain it using an example. Exogeneity means that each x variable does not depend on the dependent variable y. Income should not be dependent on expense in any way. Expense definitely is my dependent variable. It has to be a function of independent variable. However, the reverse causation should not happen. So each independent variable should not have any dependency on the dependent variable. So this is exogeneity. And sometimes what may happen is, you may have a variable, there may be a variable which is not part of the model, which is an exogenous variable, which is not part of the variable, and that variable has got influence on both the dependent and the independent, which will lead to omitted variable bias. Detecting or finding out these kind of patterns is not that easy. For example, I can say, it's just a crude example that I'm trying to give. Income expense only. We assume there is a person who drives auto rickshaw, and in a month the person makes an income of 10,000 rupees and is living happily with an expense of 8,000. Next month the fees of the children is going to come, which means expense is there. Can it drive the income of this person? Obviously it can drive. In that case, what will the person do? The person will do overtime, because there is a higher expense which is there. The person is going to do more overtime to meet the expense. So I can now say income is a function of expense, at least in the low income segment. Okay, this is an example that I am trying to say. However, it may not be highly correlated, or definitely correlation will be there, sorry, but the causation may not be that clear. But in a very small segment, there can be a reverse relationship. So this is the point it is trying to make. Difficult to identify and difficult to quantify. It is all opinion based. Rest of the things, linearity, homoscedasticity, normal errors should be normally distributed. Autocorrelation should not be there. Multicollinearity should not be there. All of these can be quantified. But exogeneity is about your own domain, difficult to identify. Okay. With this, we conclude and complete our linear regression exercise. Some of the things which I have not done, I have not taken the qualification variable, I have not taken number of earning member variable, I have not tried to make the error normally distributed. As I said that you can make the error normally distributed by removing the EMI variable, or by trying to build two separate models. We can see here that variance is not uniform. In high income, I have got more variance. Once again, I can create a flag variable. All of these are possible improvements in this. I leave all of this as an exercise for you to do and further learn linear regression. With this, I would like to say thank you. I hope all of you enjoyed learning linear regression. I request all of you to connect with us on our meetup group Data Science Mumbai. The URL for same is https://www.meetup.com/ik2analytics. Thank you.